example, say, let me make it easy. 3, 3, 1, and 1. So I've made it easy. I made it 2 by 2. I made it symmetric. And I even made it constant down the diagonal. So so the more like special properties I stick into the matrix, the more special outcome I get for the eigenvalues. For example, this symmetric matrix, I know that it'll come out with real eigenvalues. The eigenvalues will turn out to be nice real numbers. And up in our previous example, that was a symmetric matrix. Yeah, actually, while we're at it, that was a symmetric matrix. Its eigenvalues were nice real numbers, 1 and minus 1. And do you notice anything about its eigenvectors? Anything particular about those two vectors, 1, 1 and minus 1, 1? They just happen to be? No, I can't say they just happen to be, because that's the whole point is that they had to be. What? What are they? They're perpendicular. The vector, if I see a vector 1, 1 and a minus 1, 1, my mind immediately takes that dot product. It's 0. Those vectors are perpendicular. That'll happen here too. Well, let's find the eigenvalues. Actually, my example's too easy. My example is too easy. Let me tell you in advance what's going to happen. May I? Or shall I do the determinant of A minus lambda and then point out at the end? Will you remind me after I found the eigenvalues to say why they were easy from the example we did? Okay, let's do the job here. Let's compute determinant of A minus lambda I. So that's a determinant. And what is this thing? It's the matrix A with lambda removed from the diagonal. So the diagonal matrix is shifted, and then I'm taking the determinant. Okay, so I multiply this out. So what is that determinant? You notice I didn't take lambda away from all the entries. It's lambda I, so it's lambda along the diagonal. So I get 3 minus lambda squared and then minus 1, right? And I want that to be 0. Well, I'm going to simplify it. And what will I get? So if I multiply this out, I get lambda squared minus 6 lambda plus what? Plus 8. And that I'm going to set to 0. And I'm going to solve it. So, and it's a quadratic equation. I can use factorization. I can use the quadratic formula. I'll get 2 lambdas. Before I do it, tell me, what's that number 6 that's showing up in this equation? It's the trace. That number 6 is 3 plus 3. And while we're at it, what's the number 8 that's showing up in this equation? It's the determinant. Our matrix has determinant 8. So in a 2 by 2 case, it's really nice. It's lambda squared minus the trace times lambda. The trace is the linear coefficient, plus the determinant, the constant term. Okay, so can we find the roots? I guess the easy way is to factor that as something times something. If we couldn't factor it, then we'd have to use the old b squared minus 4ac formula, but I think we can factor that into lambda minus what times lambda minus what? Can you do that factorization? 4 and 2? Lambda minus 4 times lambda minus 2. So the eigenvalues are 4 and 2. So the eigenvalues are, one eigenvalue, lambda 1, let's say, is 4. Lambda 2, the other eigenvalue, is 2. The eigenvalues are 4 and 2. And then I can go for the eigenvectors. You see, I got the eigenvalues first. 4 and 2. Now for the eigenvectors. So what are the eigenvectors? They're these guys in the null space when I make the matrix singular by taking 4i or 2i away. So we got to do those separately. Let me find the eigenvector for 4 first. So I'll subtract 4. So a minus 4i is, so taking 4 away, we'll put minus 1s there. And what's the point about that matrix? If 4 is an eigenvalue, then a minus 4i had better be a what kind of matrix? Singular. If that matrix isn't singular, the 4 wasn't correct. But we're okay, that matrix is singular, and what's the x now? The x is in the null space. So what's the x1 that goes with the lambda 1? So that so this is, now I'm doing ax1 is lambda 1 x1. So I took a minus lambda 1i, that's this matrix, and now I'm looking for the x1 in its null space, and who is he? What's the vector x in the null space? Of course, it's 1, 1. So that's the eigenvector that goes with that eigenvalue. Now how about the eigenvector that goes with the other eigenvalue? Can I do that with erasing? I take a minus 2i. So now I take 2 away from the diagonal, and that leaves me with a 1 and a 1. So a minus 2i has again produced a singular matrix, as it had to. I'm looking for the null space of that guy. What vector is in its null space? Well, of course, a whole line of vectors. So when I say the eigenvector, I'm not speaking correctly. There's a whole line of eigenvectors, and I just want a basis. And for a line, I just want one vector. But there's some freedom in choosing that one, but choose a reasonable one. What's a vector in the null space of that? Well, the natural vector to pick as the eigenvector with lambda 2 is minus 1, 1. If I did elimination on that vector and set the free variable to be 1, I would get minus 1 and get that eigenvector. So do you see then that I've got eigenvector, eigenvalue, eigenvector, eigenvalue for this matrix, and now comes that thing that I wanted to be reminded of. What's the relation between that problem, and let me write just above what we found here, a equals 0, 1, 1, 0. That had eigenvalues 1 and minus 1, and eigenvectors 1, 1, and eigenvector minus 1, 1. And what do you notice? How is this matrix related to that matrix? How are those two matrices related? Well, one is just 3i more than the other one, right? I just took that matrix and I took this matrix and I added 3i. So my question is, what happened to the eigenvalues and what happened to the eigenvectors? That's like the question we keep asking now in this chapter.